Now, let's look at why tree diagrams are a good way of representing and finding these conditional probabilities. So conditional probabilities, for example, the probability of A given that B has already occurred. And we often start with a drawing a tree like this, where these forks, we can call them forks because they represent choices. And the first choice we can make is, well, is this going to be an element that is part of A or an element that is not part of A? Now, the probability of A is going to be 3 out of the 15. And if we go outside of A, that would be the complement. So the probability of the complement to A equals 12 out of 15. And now we can keep branching off because, once we've chosen that something should be part of A, we need to decide, well, is it going to be part of B as well? So we have the choice between B or not B. So B or not to be. And this is where the conditional probability comes in. If we say that the probability of B, given that A happens, that's what we're looking at now. Because we've already chosen A, so given A, what is the probability of B? And we could consult our Venn diagram to find that, of course. So of all the A's, how many are B's? And that would be 1 out of 3. And likewise, the probability of not B given A, well, if we already have A, how many are not B? And that would be 2 out of the 3. Now, note that we're treating A as the universal set for this situation here. So within A, we have the choice of B or not B, and we can see that the sum of those probabilities are 1, because the total probability is 1. So let's say we're still talking about art and biology students here. If we chose, if we're talking about the students who are not taking art, that would be the A complement part, right? And okay, so we have a choice of those who study biology and those who do not. And let's look at the conditional probabilities for that. If we're talking about the probability of being a biology student, given that this student does not study art, that would be equal to 5 out of 12. And the reason for that is we're treating a complement as the universal set here. So everything that isn't in A, that's these 5 plus these 7, that's 12. So 5 out of those 12 would be biology students then. And the probability of B complement given A complement, that would be the rest that are not A. So 7 out of 12. Now, if we look at what we found in investigation 10, this is column 4, and this is column 6 from investigation 10. So the probability of A given B turned out to be the same as the probability of the intersection of A and B divided by the probability of B. And we can move things around here, because this is an equation. So we're allowed to say that, okay, the probability of the intersection equals, now this multiplied with this. So if I multiply with the probability of B on both sides, like this, then this equation is going to look like this. And this is generally true. This is always true. And if we move these A's and B's, if they switch places, we get the B first and the A afterwards. I mean, this is the situation we have in every branch of the tree here, that we multiply probability of A with the probability of B given A, and that's the probability of the intersection. So we just multiply along the branches here. 3/15 multiplied with 1/3, that's going to be 1/15. Now, the key here is to translate the intersection symbol as AND. So what is the probability of both B and A? And it doesn't really matter, by the way, whether you write A first or B first when it comes to the intersection, because it's just AND. It's A and B and A. That means the same thing. And we can use this formula consistently further down here. So we want, for this branch, we want the probability of A and B complement. So you just have to be consistent with the way you write it. And it's the same for factors. When you multiply, the sequence of the factors doesn't really matter. So this is going to be probability of A multiplied with the probability of B complement given A. And then you just put in the numbers. And to find the other intersections, we just continue down like this. And that's it.